So we're going to talk about elevation and relief, and we're going to end up today, the lab is going to be working with a type of data called LiDAR data. So we're going to and look at a LiDAR viewer, which is really kind of fun to use. So there's a question I always ask on an exam, and I'm surprised at how many people give me kind of one-sentence answers. So here's a warning. I'm going to ask you to discuss the difference between relative and absolute relief. Okay? Give examples, that kind of thing. So that would probably be like an 8-point question. So I would, as we talk about that, you can be thinking what you might add to that. So when we're looking at relief, we're really talking about the terrain and that sense of a three-dimensional quality to the landscape or to the surface. And so with latitude and longitude, we're talking about the x and the y values, or the y and the x values, if you say it that way, which are the horizontal distance, and the elevation distance is often considered a z value. And so when you get, when we were looking at creating an Esri shapefile, some people asked me, should I use a 2D or a 3D? If you had chosen 3D, your shapefile would have had something in it called a z value, which would have taken your elevation value into that data. And that would have been really nice if you wanted to drape that over a 3D model and show a real pathway. Right? So right now with Google Earth, we're just drawing straight lines, and you can't really see how much you would really walk if you were going up and down hill. But with a z value on a shapefile, you can do that. And so relief is kind of relative in a way, because if I talk about the relief in Eugene, I'm talking about probably what, Skinner's, what's the tall butte? Skinner, Spencer? Spencer's. Yeah, I'm talking about the difference between Spencer's Butte, which I have no idea what that elevation is, and the bottom land, which is I think like 355 feet. You know, so I'm just talking about that change in elevation would be the local relief of Eugene. If I'm talking about the nation, it's Mount McKinley? I don't know. Is it Denali? Oh, okay. Okay, Denali. Yeah, so Mount Denali and Death Valley would be kind of the relief in the U.S., kind of the highest and the lowest point, right? So, where am I going here? All right. So, when we think about that aspect of the surface, I use it all the time to know where I am. So when I'm hiking, sometimes, you know, I know where you know, South Sister is, so that as I'm walking around, I kind of keep that in position, so I know where I am relative to that. When I when I give people directions, you know, that relative location, I might say, you know, we're kind of east of the Cascade Range, and you know, so as long as you keep the Cascade Range on your right, you're going north, and you're good. So we use that a lot when we're just talking about places, but the details of elevation are critical for most analysis. So if we want to do anything about stream flow hydrology, if we want to look at stormwater runoff right now, one of the big concerns in Portland area is that the infrastructure that they've developed is not going to hold the expected runoff and the amount of rain that we're going to be getting. So they're looking at, you know, how do we deal with those big expanses of water, and you can see them changing. It's kind of fascinating to look at some of these holding, almost like holding ponds along the side of the road that they're developing just to slow down water and kind of hold these catchments. Bioswales. But they're not really bio if they're cement. I don't know. Yeah. Retain. Yeah. So you see a lot of that. There's one over near Amazon Parkway that they're putting in now. Is that still a bioswale, even if it's... Okay. Great. Yeah. So we use that. You need to know the slope. You know, you need to know how fast things are going to run off. You need to get that sense of catchment and what's going to run into what. When you're developing solar energy, you know, all of that is critical on upflow of air, downdrafts of air, where that's coming from, what's blocking something else from a high area. So just being able to understand elevation is critical just in any kind of planning or analysis. So when I talk about relief or elevation, there's these two concepts. One is relative and the other is absolute. And, the absolute elevation gives me a number. It gives me something I can add, subtract, multiply, compare to something else. So it is precise information, okay? The relative just gives me an impression. I can tell this is higher than that, right? So if you look at this map on the wall of the bathymetry of Crater Lake, if you're standing at this distance, you can't see the absolute relief on this map, but you can see the relative because they've used shading, right? So I can tell what's a little higher and what's a little lower, but I can't really tell by how much. So that's the general idea, and there's lots of different ways that absolute relief and relative relief can be demonstrated. Okay, so one way is that you may see a brass cap that has absolute relief, some number, and you also may see on a topographic map a spot elevation, or you may see something that has a benchmark number on a topographic map. We'll take a look at some of these in a little bit. And most of these, or all of these, are related to the mean sea level. So this kind of arbitrary place to start counting zero elevation has been the average sea level, okay? And so once we decide where to start counting, anything above that is a positive elevation, anything below that is a negative elevation. And it was just an arbitrary spot. We could have gone the average low elevation if we'd wanted, right? To start counting, or the average high elevation to start counting, but they went with the average elevation to start counting those locations. Okay, so on a topographic map, you're going to see things like this letter here that says BM, and there's a little X, and then there's a number 241. So that is 241 somethings. Okay, I don't know if it's feet. I don't know if it's meters. You'd have to look down at the legend of the map to see what the units are in. So benchmarks are really, really helpful. There's a spot elevation. It's not a benchmark. It's not a surveyed brass cap. If you looked here, you should be able to find a brass cap on this one somewhere. But this one is just somebody has surveyed this spot where the X is, and that's 220 somethings. Okay, so those are critical absolute elevation values that you'll find on topographic maps. On bathymetric maps, or using water readings, they're called soundings, and these are not average sea level, mean sea level. Okay, they use the high or the low level for water. Why do you think they use the low water sounding? What do you mean tide? Yeah, so that's what they use. They use the low water tide for this. This 59 is 59 fathoms or 59 feet below the lowest water. Why would you think that would be more important to use? Brett, what do you think? Right. That's the most critical part, right? Because I don't want to touch bottom on a ship. So I don't care what the high is. I need to know what the low is. So that's where they use the low. Yeah. Yeah. 4. Okay. Okay. All right. Cool. All right. So soundings and spot elevations or elevations can be joined with these lines called isolines. And an isoline is a line of continuous value. So in topographic maps, we have contour lines. Air pressure maps would be isobars, temperature isotherms, and the seafloor are isobaths. So if I go back? Does it have? Yeah. So this line is an isobath, and in theory, if I were able to walk along this line, I would be at a constant 50 fathoms below the low sea level. Okay, it would almost be like walking a flat terrain, right? I would not gain or lose any elevation along that line. Okay, so with and air pressure is the same idea. So I've got high pressure isobar, and so supposedly anywhere along that line the pressure would be the same. Okay, so we use that same concept with topographic maps. And so with a topographic map, they used to start out by going out in the field and surveying elevation points. Okay, so each of these dots had a value of the elevation at that point, and then cartographers would go back and kind of extrapolate what would be 40 feet. If this was 40 feet and this is 40 feet and this is 35 feet, my 40 is going to be somewhere around in here. And so they would create these contour lines of equal elevation kind of going through the dot to dots. And some would go exactly through a point, and some would kind of get as close as they could between a couple points. And so you would end up with a contour map showing elevation across this area. And the difference between the lines is called the contour interval. So for this map, this map changes 10 feet as you go up or change each line. And so you've got this ability to kind of show the change in the landscape based on this extrapolated elevation. So if you look at it kind of in a little 2D sketch, and the contour interval for this is 500 feet. So here I am on this island at sea level, right down here, and the first contour line then is 500 feet above sea level, then 1,000 feet above sea level, 15 feet above sea level, all the way to the top line, which is 3,000 feet above sea level. And I'm just looking at this one right here. Yeah, I'm looking at this westernmost hill. And then somebody could have done a spot elevation that gives you the exact elevation at the top, but if that weren't here, and I asked you a question, what's the elevation of this side of the island? You could say, 3,000 feet is about all you can do. You don't know, how much more, you don't know what the next contour is. You can't really tell if you're halfway between or not. So would look at that. Now, a couple things you can notice is that slope is pretty gentle. This slope is a lot steeper. And so when I look at the contour map here, I can see that the contour lines can indicate whether an area is steep or gentle. So right down here, the contour lines are farther apart. So it takes me a little longer to get up to that new elevation every 500 feet, or 500 feet in elevation. On this side, those contour lines are really close together. And so that indicates a much more vertical cliff. And so we used to have students do these elevation profiles. Did you guys did that in watershed science, where you can take your 2D flat image and drop those contour lines and kind of build a profile so you get a sense of the landscape. And many years ago, 20-some, I did a cross-country bike trip, and that was, we were using the old bicentennial route, and we got these great topographic maps with these profiles. They meant nothing to me. I couldn't understand. I don't know. It was just like a foreign concept in that day. It's like, I don't know what those are trying to tell me. And what they were trying to tell me was this was going to be really hard. and the other thing I learned is this could be easy if you're going downhill, but if there's a headwind, it's still really hard. So anyway, but what's really nice now is Google Earth will do that for you. So here is a path in Google Earth, and you can create, especially with Pro, you can create a profile along that elevation line, and it gives you that sense of change in elevation. Okay. So some things about contour lines. They're lines of equal elevation. Okay, they're above sea level, mean sea level, and the interval is how much change happens between those lines. Okay, so if we look at a piece of a map, the other thing that you should notice is that contour lines are supposed to be closed features, right? So this is where it says 350. If I walk along this line, it would close in on itself. Okay? Now sometimes you won't get to see that because it's on the other side of the map. It's on a different maps, but if you put the two maps together, you should be able to follow that contour line. So that's one of the rules of a contour line, is that they are closed features, and every once in a while you'll find one that's wrong on a topographic map. That they didn't close it. Another really cool thing about contour lines is that you can tell if it's going uphill or downhill based on the shape of the contour line itself. So sometimes you're looking in an area and they may not have labeled some of these elevation features, or you can't really tell, is this uphill or downhill, and you have one point to view. Where your contour lines come to a point where they're more of a V, those points are pointing uphill. So this would be uphill, and where they're more bowed out, they're pointing downhill. So if you think about erosion up a ravine, those little ravines tend to be pretty narrow little cuts back in a mountain, and that's what makes those little V shapes. Right upstreams. Deposition tends to be wider and rounder, and so that's why you get that little bit of a difference on a topographic map. And it's really useful. Sometimes when you're looking at a big map, you're trying to figure out, okay, is this up or down, and which number am I counting up, am I counting down on that? And then there's the other example of the V's point uphill. So they can have kind of this gentle, gradual down at the bottom, and it's steeper up here at the top, and you can tell that by these lines get farther and farther apart, so you're kind of getting out onto flatter ground. There's several special contour lines. The index lines are the ones that are in bold and have the number. So, for instance, this one is the 300-foot index line. And if I know the contour interval, then I can count, I know what the next line's going to be, right? So if the contour interval is 50 feet, then, and this is 300, then this could be 350. This would be 400, 450. And I'm just assuming that because this is lower, so I'm just assuming I'm going up here, but I would have to really look around and figure, yep, those were pointing up, so that's moving up elevation. So if this is 300, then this would be 250, and then on down like that. Sometimes there are supplemental contour lines, and you see that a lot in the valley where there's a large expanse of in I think here are some other supplemental contours. So there's not a lot of change over a large distance, so you might have a dotted line or a dashed line is only a 10-foot contour. So you'll see all of that information on your topographic map. And then there are depression lines. And are you depressed yet? Some of you might be. But the depression contour looks like the little sandworm in Dune or Tremors. If you've seen Tremors, it looks like that thing. So it's a circle with kind of these perpendicular hatch lines or tick marks that look like teeth pointing into that. And what that indicates is a depression. The interesting thing about a depression contour is when do you start counting, subtracting that elevation? And so, well, no, you can find an index contour. So let's say I have all of these labeled. So there's 600 feet, 800 feet, 1,000 feet, 1,200 feet. And then I come to my first depression contour. This elevation is the same as my last non-depression contour. Okay, so this is kind of the edge where it starts to go down. It hasn't gone down yet. So then that's a tricky one. People want to take that, down that, what am I doing, 200 feet. So a lot of people would label this one as 1,000 and this one is 800, when in reality, your first depression contour means you haven't changed, you're just getting ready to. Here's the edge. And you go down too. Okay. And so here's more supplementals, dots and dashes. All of those will be identified. There's a depression contour on your topographic map. So let's get out the Three Sisters maps and take a look at a couple things. Okay, so this is a 15-minute map. So it covers twice the area of the Eugene East map. So it's 15 minutes in latitude, 15 minutes in longitude, right? And if you look at this map, instead of 2.5 minutes, you can see, let's see if I can magnify right here. Oh, no, I didn't want to do that. It goes up to, its first indicator is 5 minutes, right? So, yeah, so there's 5 minutes? Yeah, 5 minutes. So this would be 44 degrees, 5 minutes north. And if I go to the southern edge of the map, I've got 121 degrees, 45 minutes. And somewhere here there should be another 5 minutes. Ooh. Yeah, so that's 121 degrees, 50 minutes west. So I've got, so it's covering just twice as much area. So why don't you go to, let's see if we can find, let's just find an easy one. This one, Caustic Butte. So it is in section 8. Let's see, township, 18 south, and I'm not sure what the range is. Everybody find that? Range 7 east? 8 east? Okay, great. And so you can see 6,000, oh gosh, are we in feet or meters? You have to go down and look at the bottom of the map. And it will tell you, your contour interval is 80 feet. So between all of those contours, you have to have your multiplication by 8 down. Really good. I know. I like the 20 a whole lot better, or the 50s. Okay, so this the index line is 6,000 feet. Okay, so what would this next contour line right here where the hand is be? Okay, are you sure which way is up and which way is down? So what I would need to do is go find another contour. So you're right. So here's the 5,600. And then there's the 6,000. So yeah, so this one right here would be 6,080 feet, right? So what would this guy right here, this little circle, be? Right, so you're just going to add another 80, right? So that's pretty simple. I see a benchmark here that gives me the elevation. Right on that section line, yeah. And then I see another benchmark at Tie Creek.
I got a question.
Yes, sir.
So stick view thing, whatever it is.
Yeah.
All those little circles inside of it, those are all the same.
Yes. Yeah. Yeah. So they're just like, it's real hummocky right there. That's what you could get from that. Exactly. Exactly.
There would be lines.
Is 1 second. 1 second. Yeah. It does? Okay. And Ed, what was your question?
If it was any higher, there would be lines inside that, or if it was lower, there would be actually depression.
Right, right. Yeah. So if this was higher than 6,160, right? This would have an extra line inside. So all of these, these are all the same elevation, those little humps right there. Okay? Is there anything else interesting on this map? Let's take a look here. I'm going to zoom out.
I like this lava flow.
Right, where are you? Can you give us a location?
It's kind of the north third of the map.
No. Give us Township Ranger, lat long.
Yeah, it's Township 16.
Okay.
Range 8 east.
Oh, nice. And a section or no section?
It's kind of barely in a section.
Okay. So are we looking at the lava flow right here?
Yeah.
Okay.
I just think it's cool how you can see it flow all the way down that little valley.
Yeah. And so check the idea that the pointy edge is pointing up a hill. Linton Lake is a great one for that. So let's just look here. So yeah, you can see that stream is coming from 5,200 to 4,400, but those points are pointing in the direction uphill, right? So that's just a really nice clue when you're looking at a map and you're trying to figure out, okay, am I pointing up or down? And these right here are kind of pointing down the hill. So so there's benchmarks all over down here. This is that glacial trough from that the old Mackenzie Highway goes up. So there's lots of absolute elevation. The contour lines show absolute elevation, even though they're somewhat extrapolated. We count those as absolute elevation. The benchmarks are absolute. The spot locations are absolute. So go to the top of the sisters. One of those sisters. Where are they? There was an elevation. Where am I going? Three Sisters. Here we go. This one. South. Go to South Sisters. It's a VABM. So it's a benchmark, but it's not surveyed in. I think it is satellite elevation set. So we'll have to look that up. But it's a different kind of spot elevation. Yeah. So that's the point elevation for that. Yeah. So if I gave you this, which side of South Sister is more steep, the north side or the south side? Yeah. See those lines? They're almost merging, right? That's really sheer. And I couldn't even get up this side. Too much screech. Yeah. Right. So you can see that. Let's see, anything? I think there might be a crater on this, but maybe not. Let's see. Yeah, but I don't see any depression in this. I think there was one. Let me see if I can find one. I know, but it may not be big enough to show on here. I don't think so. A depression crater, no. Really? Okay. Range 8. Section who? Ah, there we go. Devil's Garden. Nice. That wasn't it? Oh, it's right below it. Yeah. Good job. Good eye on that. So here we go. The Devil's Garden has a depression, and the Catsup Butte has a depression. Nice. I know. So what's the difference between the two? How much change is in elevation between the two index lines? Between the two index lines. So I've got 1, 2, 3, 4, 5 times 80, right? So that's a nice thing. You can count up by 400 and not have to count every index line. So if this is 5, 6, this would be 5, 6, 400. And then I've got 1, 2. So the beginning of that elevation would be here. Right? So it's really nice to figure out what is the overall change between those index lines, and that lets you add things up really quickly instead of having to count every contour. Okay. So we can work on that. So on it, oh, that's really fuzzy. That's a, can you read that? It's a spot elevation. So somebody has surveyed in that spot, and that is the elevation for that X. Okay, 6158.
6158.
Yeah. Yeah. So, no, it would have BM. It would have the letters B and M and an X to be a benchmark.
So is the one thicker line?
This one up,
Is that 57?
which one?
Is that
56, and then this would be 80 more, 80 more. So this would be 5,600, 6,000. Yeah, 6,000 right there. I added wrong. You can so correct that, Derek, next. Yeah. And then, so there would be the benchmark. You see that one where it has that beside it. Okay? So, which one? This one here? One that's going under the 8.
That's right at 6,000 feet. That's why it's thicker, the red line.
I'm going to try and zoom out on this. Hold on. Yeah. Okay, so ask the question again, Ed.
You know, there's 56 thick red line, and the next thick line is underneath the 8.
56. Oh, so that's another index line. Yeah, but it doesn't have the value on it. You'd have to, you just know that that is 5 increments, right? So they don't label every index line. Okay? Yes, then all you have are numbers, right? So, yeah. So they can have a label, but they're really nice for counting by 400. So all I have to do is, if I have 8 index lines, I could just multiply 8 times 400 and get that. Okay? So, for instance, right through here, there's one index, there's another 400 feet, there's another 400 feet. So I would know what the T in the butte. If I asked you the elevation of the T, the most you can give me is this index line, right? If you were somewhere between 2 index lines, you could conceivably say halfway. Okay? If I were pointing at let me see if there's a good example here. All right, let me see if I can get to this K right there. So if I were saying the bottom of this K, what is the elevation? You know this and you know that, so it would be reasonable if you wanted to extrapolate, but I would go with, one of the two. Yeah. No, I don't know if 17 would work, but maybe. They're 80. Okay. How come shift? Yeah. Nope. Okay. Anyway, so on the exam, where is my view? Actual page. Okay. So on the exam, I would give you a lat and a long, and I would ask you to tell me the elevation, or I might give you have an arrow pointing and saying, what is the contour interval and the lat and long for this. So it'll just be working with the map and giving me all that information. What's the township range and section? What's the lat long? What's the elevation? Which side is steeper? Blah, blah, blah. Okay? So, all that fun stuff that you get to practice. So I'd be glad to help with that. And you can look at it on the Eugene East map as well. It gets a little more confusing because there are so many other lines on that, with city lines and that kind of stuff. So relative relief really provides context. It gives that three-dimensional effect. And you can do that by raised relief or by shading. There's lots of different ways to show that. Could be. So here is a raised relief that just kind of gives you a sense of this is way taller than that. So on this globe, that raised relief is really exaggerated. Here's a relief model. So I can't really tell you how much taller the valley is than the mountains. I could maybe say 50%, taller, but I don't have any real numbers with relative relief. Here's a nice one where they've kind of combined contour lines on top of a raised relief map. And so that gives you both aspects. Here's just shaded relief of the U.S. So this is done with something called a digital elevation model, and we'll play with those a little bit maybe next week. So I don't know how much, I just know that it's higher. Here's another one that doesn't give me detailed information, but using shadows and shading, it gives me that sense of relief, so I can tell kind of what is steep side, what is a gentle side, which is higher. Again, I can't do anything mathematical with it. And here's a nice combination where they've used the contour lines plus shading. So, and this is really nice sometimes when people are learning to use a map, because you can see that's higher or that's steeper based on the shadows or the shading on that map. I quite like the color shading in this. That really adds this really steep edge, on that arete here, and then the Cirque Lakes down through the side. Here's a nice one of Crater Lake using contours and shading again. So often they're used in combination. So one of the things that people do currently is that they use what's called a digital elevation model. So what we've been using before, the data that we added to ArcGIS Online or the data that we collected in Google Earth, has been considered vector data model. We've been using points, lines, or polygons. So when we did a waypoint, that was a point. If we had done a path or distance from one place to another, that's a line, and then you all created lake polygons. And this is one data type, one data model. For a digital elevation model, they use what's called a raster data model. And basically, they take an area, they being cartographers or geodeticists or something. Anyway, they use an area and create a grid that goes over the area. And each grid has one value. And for an elevation model, the value of that grid is the elevation. So a digital elevation model is not as precise when you're looking at the real shape of the land and the details, because they've kind of generalized from one feature to the next. So this is a digital elevation model that's showing you those grids and how each grid has a different elevation, and they've kind of extruded that elevation with a column. So you can see that the blue is a higher elevation and the red is the lowest elevation. And if they drape that and smooth those connections out, it makes that 3D much smoother look. And that's what you were looking at when we were looking at this map. That's a digital elevation model that has shown each of those. If you zoomed in here, just tiny, tiny squares, and each square has an elevation value. So I blew up an elevation model, and I'm not sure you can see too much on. I wish we had the whole TV thing where you could, but maybe when you look at the video, you'll be able to see that. But there are, can I make I'm going to make a shape here. So there are a bunch of squares here, and each square is about that size, okay? So, and each square, if I were to click on it in ArcGIS, it would give me a value and tell me what is the value or the elevation for the center of that square. So from a digital elevation model, then, you can get all kinds of products called derived products. So you can get a slope, you can get an aspect that you would use for, let's say, if you want to put in solar panels, if you want to figure stream runoff, you need slope. If you want to figure out what tributaries and channels, you can do that with a DEM. So these are really powerful data types. So currently, the newest DEM model is called LIDAR. And some of these DEMs, like there's a DEM of climate in the US, and each square is 1,000 kilometers by 1,000 kilometers. So you can imagine if you had to pick one temperature average for 1,000 by 1,000 kilometers, right? So that's really generalizing, right? Or the elevation. So the elevation model of the whole US, where did that one go? If you could zoom in on this, each of those squares is probably 500 miles by 500 miles. So they're trying to figure out what is the elevation average for that 500 miles by 500 miles, which is a huge generalization, right? So DEMs can be really coarse. The new thing right now is LIDAR, which is amazingly detailed. So LIDAR stands for Light Detection and Ranging, and this is created by a remote sensing product, so some kind of machine that sends out a laser pulse, and it collects millions of data points in minutes. So it'll send a laser down to the earth, and the time it takes that laser pulse to return is the distance between the apparatus and the surface of the earth, right? So it records the distance of the top of buildings, the distance between the building and the ground surface. So it sends out 400,000 laser pulses per second. So it's getting back 400,000 data points every second. It's just huge. These things are huge. The Willamette Valley LIDAR set, I think, is over 3 terabytes. I can only download little pieces of it at a time. It's just huge. So when the LIDAR pulse gets sent out, it can hit the ground. So if nothing's in between the LIDAR and the ground, that's called a bare earth hit. Or if it gets returned from the top of a building, or it can get returned from the top of trees. And based on all of that data, you can create amazing images. So here are 2 images. The DEM on the right is Mount St. Helens, and the size of the grids, the size of the cells is 10 meters by 10 meters, which is pretty good resolution. But the LIDAR data on the left, the size of the cell is 0.5 meter. So, and you can just really see how much more detail you can get with that 0.5 meter LIDAR. So do you guys remember the Oso landslide a couple years ago that wiped out the town of Oso? Yeah. So one of the things that they discovered after the slide is they ran LIDAR images all along that ridge line, and they found out that that whole area is filled with old landslide cracks, and that's what activated in the OSO slide. But you couldn't see them with a DEM that's 10 meters, but when they ran it with LiDAR, they were able to see all of those potential other landslides. So now they're using that more often to kind of look at very large-scale analysis. Okay, so there you go. Hold on.